Hello again, and welcome to Advanced Physics for High School Students. This is Lesson 73, and it is entitled Magnetism III, Faraday's Law and Lenz's Law. In this lesson, I'm going to describe to you something that many folks think is the most difficult of this entire course. You will need time to digest it, and if you think that what you're going to see is crazy, then you're not alone. The good news is that, conceptually, the course is not going to become any more difficult. Remember that in about 1819, Hans Christian Ørsted discovered that a steady current produces a steady magnetic field, connecting electricity with magnetism for the first time. A little later, Michael Faraday suggested that maybe a steady magnetic field could produce a steady current, and he did many experiments to look for that. It turned out not to be so. One of his experiments can be described this way. Faraday connected a battery to a switch and a solenoid. He closed the switch, allowing current to flow through the solenoid, creating a magnetic field in the solenoid. Maybe the magnetic field runs is indicated in this diagram. It depends on the direction of the current, and it depends on which way the solenoid is wound. He put another second loop of wire around the solenoid. Let's call this one loop number 2, and we can call the original one loop number 1 with a solenoid. Whenever there was a current in number 1, he never managed to see a current in number 2. If there's a current going in number 1, there is a magnetic field in the solenoid, and that magnetic field also passes through loop number 2. But Faraday never saw any current in loop number 2. So he concluded that a steady magnetic field as produced by the solenoid in circuit 1 does not produce a steady current in number 2. But then, one day he noticed that as he closed the switch in circuit number 1, he saw a current in number 2. And when he opened the switch again in circuit number 1, he saw a current in number 2. And now, therefore, he concluded that a changing magnetic field causes a current. It's not a steady magnetic field, but a changing magnetic field. And this was a profound discovery which changed our world, contributing largely to the technological revolution of the late 19th and early 20th centuries. The current, and therefore an electric field, can be produced by a changing magnetic field, and that phenomenon is called electromagnetic induction, and it runs our economy. Electromagnetic induction can be produced in other ways. For instance, a loop of wire can be connected to a galvanometer, which is essentially a very sensitive ammeter, a voltmeter, and a magnet can be waved around nearby the coil. As the magnet is waved, then the magnetic field changes across the face of the coil, and the galvanometer needle deflects. This is actually an activity that you may have an opportunity to do sometime in the laboratory. When the magnet approaches the coil, the needle of the galvanometer moves one way, and when the magnet moves away from the coil, the needle moves in the opposite direction. Quantitatively, Faraday developed the idea of magnetic flux. We symbol magnetic flux mathematically with the Greek letter capital Phi and a subscript B. You can also have electric flux, which will be a Phi with a subscript E, and you can have gravitational flux of capital Phi with a subscript G. We're talking about magnetic flux. Figuratively, you can think of magnetic flux as sunshine going through a window. Here is a short narrated animation to describe magnetic flux.
When magnetic field lines pass through a flat surface, we can define a quantity called the magnetic flux that represents the number of field lines penetrating it. If the surface is rotated about the field lines, the magnetic flux does not change. However, the flux does change if the area changes. The flux also changes if the surface is tilted, falling to 0 when the surface vector is perpendicular to the field lines. The cosine theta term in the equation accounts for this. When rotated past 90 degrees, the surface normal vector and the magnetic field vectors are in generally opposite directions. Now the flux is negative. Any surface can be built out of many tiny surfaces. So by letting the square become infinitesimally small, we can use calculus to define the magnetic flux through any surface.
As was stated in that short animation clip, The magnetic flux phi b is defined to be the dot product of the magnetic field vector B with the area vector A. So in this diagram over here, you can imagine these blue lines to be the magnetic field lines, and passing through this area here, which has some radius, so pi r squared is going to be the area, and you could imagine an area vector A that's defined to be an arrow that is perpendicular to the surface and represents the direction that the surface opens up. Then there could be an angle between the direction of the magnetic field lines and the direction of the area, so that you could rewrite the magnetic flux in terms of the magnitudes of the vectors. It's going to be the magnitude of B times the magnitude of A times the cosine of the angle between B and A. And in 95% of the numerical problems you're going to work, the angle is going to be 0 degrees, so that the cosine is equal to 1. But in some problems, that area may be tilted at some angle, and if it is, then you have to account for that with the cosine factor. The units for magnetic flux are Teslas times square meters, and that unit is often called a Weber, named after a German scientist and abbreviated WB. Now, Faraday described mathematically what he saw in terms of a voltage that was induced in a coil, stated mathematically what we now know as Faraday's law of electromagnetic induction. Faraday's law relates the EMF induced in a conductor, usually a bunch of wire loops, and the changing magnetic flux through the loop. Mathematically, we write Faraday's law this way. In this expression, E stands for the EMF that's induced in the coil, the voltage essentially that I measure, and that would be measured in volts. That's the thing that essentially measures the electric field that's induced in the loop. N stands for the number of turns that are in the conductor, the number of loops of wire in the coil. The delta phi b is the change in the magnetic flux. It could be that the flux is changing as a result of a changing magnetic field, or it might be that the flux is changing because the size of the area of the coil is changing. Or it could be that the flux is changing as a result of a change in the angle between the magnetic field and the area of the coil. And in fact, it's that last thing, the changing of an angle, say by rotating the coil in the magnetic field, that is most commonly done in terms of generating electricity. That's the way TVA gets its electricity. And delta t is the time interval over which that changing magnetic flux occurs. Now you'll also notice that there's a negative sign in Faraday's law. It's there due to the direction of the induced current produced by the changing magnetic field, and its presence in the equation is an expression of Lenz's law. In words, Lenz's law says this: the induced EMF always produces a current whose magnetic flux opposes the original change in the magnetic flux. Let's try to illustrate it in this way. I have a conducting wire, a square. I could have chosen any other shape I wanted to. Let's try to see this loop three-dimensionally. And I approach this conducting wire with a bar magnet. The bar magnet has a magnetic field that runs according to these yellow lines. As the North Pole approaches the loop, the direction of the magnetic field is downward. As I approach the loop, the conducting wire moving the bar magnet, that's essential. I can't hold the bar magnet still. I have to move it. If I come down from above and I move the magnet down, you're going to see a current going through this loop, a current that's being induced. The magnetic field is getting stronger and stronger as it passes through that loop. So the magnetic flux is increasing. It's changing. Faraday's law says that when this magnetic flux changes, there's going to be an induced EMF that drives a current. Lenz's law says that the current that's in the loop is going to produce a magnetic field that opposes the changes in the flux. Well, what's happening? The flux is getting stronger. As the flux gets stronger, the coil is not happy. It wants to keep the flux the way that it was. So it's going to create its own magnetic field to try to oppose that change in the flux. That induced magnetic field has to be caused by something, and what's causing it is the induced current in that coil. And according to the right-hand rule, the induced current is going to run in a counterclockwise direction if I look at the coil from the top. The magnetic field from the bar magnet is in the downward direction, and as it is increasing the magnetic flux through the area of the coil, as I move the bar magnet in, the current in the loop produces a magnetic field that's in the upward direction when you look at the loop from above. Now, if I pull the magnet out and watch what happens, I'm going to see that the induced current is going to flow in the opposite direction. If the magnet starts close to the coil, then there are lots of magnetic field lines from the green bar magnet penetrating the coil, so the magnetic flux is high. Now, if I move the magnet away from the coil, that magnetic flux is going to decrease. It's going to change. What's happening to the magnetic flux? It's getting weaker and weaker because fewer and fewer magnetic field lines are penetrating through the coil. What does the coil do? It tries to oppose the change in the magnetic flux. It wants to keep the magnetic flux strong. So it induces a magnetic field of its own as a result of an induced current flowing in the coil. What's the direction of that induced magnetic field? It's in a direction to oppose the direction of the changing flux. The magnetic field lines due to the green bar magnet are in the downward direction. They're getting weaker and weaker as the magnet moves away from the coil. So the induced magnetic field is going to be in that same direction to try to keep the magnetic field strong, opposing the decreasing magnetic flux. In order to create that induced magnetic field, then I have to have an induced current. And which way does that induced current flow? If it's a conventional current, the right-hand rule tells me that the induced current flows in the clockwise direction as viewed from above. I summarize Lenz's law with the words, maintain, man, maintain. Here's what I mean. The loop wants to maintain the magnetic flux the way that it was before the magnetism started changing through the loop. If the flux were originally weak, the loop tries to maintain weak magnetic flux. On the other hand, if the flux were originally large, then the loop tries to maintain strong magnetic flux. How does it do that? By creating its own magnetic field. The induced current wants to oppose the change in the magnetic field. That's Lenz's law. It's the most human law in physics because there's inertia in all of us. We all fight change at some level, and the loop fights change in the magnetic flux. Lenz's law is extremely powerful in determining which direction these induced currents will run. It's not a quantitative law. You can't calculate how strong the current will be, but it's very useful to know the direction of that current. That gets you out of all kinds of problems with minus signs. Practically speaking, when I make calculations using Faraday's law, I completely disregard the negative sign and I only work with magnitudes. After the calculation is finished, if the question requires it, I apply Lenz's law to figure out the direction of the induced current. Here's how I do it. I ask myself a series of questions. Question number 1. Is the magnetic flux changing? If it's not changing, then there's not going to be any induced current, and the question's over. But if there is, and 9 times out of 10 there will be, then the next question, number 2, is this. Is the magnetic flux increasing or is it decreasing? If the magnetic flux is increasing, then the induced magnetic field is going to be in the opposite direction to the changing magnetic field. On the other hand, if the magnetic flux is decreasing, then the induced magnetic field's direction is going to be in the same direction as the changing magnetic field. Next question, number 3. What is the direction of the changing magnetic field? Remember, we define the direction of a magnetic field to be the direction that the north pole of a compass would point when it's placed in the field. So, which way does the north pole of the compass point as a result of this changing magnetic field? That, combined with question number 2, is going to give me the answer that I need to know about the direction of my induced magnetic field. And that leads me to question number 4. Applying the appropriate right-hand rule, what is the direction of the induced current that sets up the induced magnetic field? To figure that out, I have to apply the appropriate hand rule, either right hand or left hand, to figure that direction out.